A modified Atwood machine is set up on a horizontal surface or an incline. But we're going to treat it the same way. We're going to take a system approach, and we're going to choose the direction the system will accelerate and call that the positive direction for our coordinate system. In this scenario, we're dealing with a frictionless surface. Therefore, we can predict the direction of the acceleration as shown by the arrow. Now, I'm going to identify these as objects 1 and 2, and let's go ahead and do free body diagrams for each object in our system as they accelerate. Let's start with object 1 and label those 3 forces. Then let's look at object 2 and label these 2 forces. And what I want you to notice is that my tension forces up here are the same in their magnitude. Now let's go ahead and sum forces for the system, recalling our predefined positive direction. So T1 is in the positive direction of the acceleration that way, whereas T2 is in the opposite direction of the acceleration. Likewise, mass 2 multiplied by the acceleration due to gravity is also in our positive direction. So we will subtract T2 from T1 and add mass 2 times little g. Then we're going to set that equal to the mass of our system, M1 plus M2, where both masses are the same. Each mass is 2 kilograms. Next, we're going to solve for the acceleration of the system. Why? For the same reasons we did on a normal Atwood machine problem. Once we know the acceleration of the system and acknowledge that mass 1 and mass 2 share this common acceleration, we can then analyze each object separately. So, masses are identical, both 2 kilograms, so if we have these numbers, we can then put it into our equation. I want you to again make note, we have 4 kilograms in the denominator. Okay? That is very important. We've summed the masses and placed those into the denominator. Now, the acceleration of the system when we solve this would be 5 meters per second per second. Now let's take that information and now let's analyze these objects individually. Let's start with mass 1. For mass 1, there's only one force, the force of tension. So that means we're going to set force of tension equal to mass times acceleration. And we found the acceleration of the system to be 5 meters per second squared. That means the acceleration of this object is also 5 meters per second squared. We can solve this to get the tension force as 10 newtons. Now, you know in the previous video I taught and showed you how these tension forces when accelerating are equal in magnitude, opposite in direction. Let's look at that again. So let's solve for T2, and we can predict that T2 will be less than 20 newtons. We can say that because if it were not accelerating, T2 would be 20 newtons, 2 times the acceleration due to gravity. I predict it'll be less than that. So now we can solve this problem, isolate T2, and go ahead and solve this to be equal to 10 newtons. And I want you to think about it. It's exactly half of what it would have been if it was not accelerating. Well, look at the acceleration of the system. It is exactly half the value of the acceleration due to gravity. And it makes sense since mass 2 is accelerating in the same direction as the acceleration due to gravity. Again, analogous to what we talked about with apparent weight. Okay? Now, in this scenario, we have friction. And this is the force of kinetic friction because this system will accelerate. Okay, so I'm telling you that it will accelerate. So I've added to the free body diagram the force of kinetic friction because it will be in motion. Let's sum the forces for the system. We have our same direction defined as positive. So pause the video and look at my summation here. Also notice I'm taking the sum of the masses again because this is a system summation. So I'm going to solve for the acceleration of the system. However, I run into an issue here, this force of kinetic friction. Since the system's accelerating, I need to figure out the force of kinetic friction, which brings me to a major misconception in these problems. Many students believe that the vertical forces acting on mass 1, the object that is on this horizontal surface, don't play a factor. Well, actually, they do. They do because remember how we calculate the force of friction. For an object on a horizontal surface, if we sum the forces vertically, we can show that force normal is equal in magnitude to the force of gravity. We can then use the physics is fun equation to substitute m1g and to ultimately solve for the force of kinetic friction. Okay, so when we sub in m1g, which is force normal, for the mass on the surface, we can then solve for the force of kinetic friction and find it to be 2 newtons. So let's go ahead now and take our 2 Newton frictional force, which is in the opposite direction of the acceleration of the system, and let's add it to our summation here. So we essentially have 20 minus 2 on the left side, which gives us 18 in the numerator. We divide by the mass of the system in the denominator of 4 kilograms, and we find the acceleration of the system to be 4.5 meters per second squared. Extra credit opportunity, first thing tomorrow morning. Please come in and tell me and show me your calculations for tension force 1 and tension force 2 when the system is accelerating. In this scenario, we have a third mass that is attached to the table, preventing the system from accelerating. We are going back to mu equals 0, which means this is a smooth, frictionless surface. Now, M3, again, is physically attached, and because it is attached, it prevents the system from accelerating. Here we have the free body diagrams for objects 1 and 2 when accelerating. Now, when the objects are not accelerating, look at the tension force. Notice they are greater in magnitude. In fact, they would be 20 newtons when they're not accelerating. So, let's ask the question, what is the force of block 3, the one that's attached to the table, onto block 1? And I know what you're thinking. This is yet another application of Newton's third law. So we're going to look at these mutual force pairs. In this case, we're going to look at one mutual pair, and that would be between object 1 and object 3, where we can state that the force of object 3 onto 1 is equal in magnitude but opposite in direction to the force of 1 onto 3. So we know the tension force to be the weight of block 2. So that would be 2 kilograms multiplied by 10 meters per second because the object is not accelerating. So that would be 20 newtons. What does that mean? Well, if the tension force is 20 newtons to the right for object 1, then doesn't that mean that the force of 3 onto 1 back is negative 20 newtons? Remember, the force of tension right here is a positive 20 newtons. Positive because it's in the same direction as our system acceleration. So the action-reaction pair here would be that The third object exerts a leftward force of 20 newtons onto mass 1. So I've added this additional force now to the free body diagram and labeled it as the force of block 3 on the block 1. Notice it's going to the left. So in this video, we've taken yet a complex problem, and we've now looked at it through the lens of a modified Atwood machine. And in class, you're actually going to take it to the next level and look at modified Atwood machines, which are on an incline. And those are a lot of fun. I'll see you guys in class.